In today's lecture, we are going to discuss a very important phenomenon which occurs in case of all types of waves. When you talk about a mechanical wave or a non-mechanical wave, and in case of mechanical wave, a longitudinal wave or transverse wave, in any type of wave, this phenomenon takes place. What is actually that phenomenon? In fact, we are talking about interference of wave. When you study optics, you study interference of light. Here, our present concern is for the general theory of interference regarding any wave. Although we will see later on the particular interference in case of sound wave, which is a mechanical wave. But it also takes place in any type of wave. Okay. Actually, this lecture will be completed in two parts. This is actually the first part of the lecture on interference of wave, because you will see in this lecture we will derive only the basic equation for the resultant intensity, on the basis of which we explain the interference of wave in a clear-cut manner. And after this first part of the lecture on this interference of wave, we will see the important points of discussion in its second part. Because I will try to cover all these things in one video, the video will become lengthy and that will be not suitable for you. Okay. But when you have to ask a question regarding this interference, particularly long answer type question, then you have to write all those things which I will taught in both of these videos. So watch this video seriously, and after this, when I will publish the second part of this lecture, you also must watch that. Because after watching these two videos, the total concept of interference of wave will be completed. Okay. So now let us see, first of all, what is this interference? As a phenomenon, what is interference? Let us see. Actually, I am not defining this phenomenon interference directly, but before knowing the definition, let us see something. You can see this figure. I have shown here this S1 which has been marked by a dot. Actually, this S1 represents a source of wave. It may be a source of light wave, it may be a source of sound wave, okay, any type of wave. And S2 is actually another source. And let us say that actually these two sources are not very far apart from one another, but they are very close. Okay. Although in figure they have been shown separately by a large amount, but mentally you can think that S1 and S2 are lying almost at same position. So the waves produced by S1 and S2 will move almost in same direction. Okay. And in course of the motion of the wave from S1 and S2, they will get superposed. So there may be several points in this region where superposition of the waves from S1 and S2 will take place. Actually, in this figure, I have shown only one point P, where I have shown that the wave from S1 and S2 get superposed. But don't think that this point P is a unique point. There may be several points in this region where these waves from S1 and S2 will get superposed. But for knowing the definition of interference, I have considered only one point. Okay. So let us say that the wave from S1 and S2 gets superposed at this point P. I hope you have an idea of the intensity of a wave. You know how intensity of a wave is defined. Intensity of any wave is defined as the amount of energy which passes through unit area of a surface kept normal to the direction of propagation of the wave in unit time. So energy passing through unit area in unit time normal to the surface, that is called intensity. Okay. So for any wave, actually wave always carries energy. So always we define intensity for any wave. So now let us consider that the intensity of the wave from S1 at this point P is I1. In fact, intensity of a wave at different position will be different. So you must say that I1 is the intensity of the first wave, that is wave from the source S1 at point P. And at the same point P, the intensity of the wave produced by the source S2, which you can say second wave, that is equal to I2. It is okay? Very simple. I1, this is intensity of the first wave, and I2 is intensity of the second wave. At which point? At the point P. Now, when the waves from S1 and S2, marked by this 1 and 2, will reach to the point P, they will get superposed. They will meet each other. Okay? And when two or more waves are get superposed, a resulting wave is produced. So definitely after the superposition of two waves at point P, a resultant wave will be produced. Okay? And now if you consider that I is the intensity of that resultant wave which has been produced by the superposition of wave number 1 and wave number 2. In other words, you can also say that this I is the resultant intensity at point P. As intensity is a scalar quantity, energy is a scalar quantity, so commonly people think that if I1 is the intensity of the first wave, I2 is the intensity of the second wave at point P, then when these two waves will get superposed at point P, then the resultant intensity should be simply the sum of the intensities of the two waves. That is, I should be equal to I1 plus I2. Common people think like that. But physics says the phenomenon is not like that. You can't say that if I1 and I2 are the intensities of the two waves, then I1 plus I2 will be definitely the resultant intensity at point P at the point of superposition. If you say like that, you are wrong. The real situation is different. In fact, what will be the resultant intensity at this point? That depends on the phase difference between the two waves superposing at point P. It is seen, I will just explain after this definition of interference what I am going to talk to you just now. If you say that the resultant intensity at point P is not always I1 plus I2, it means it may be I1 plus I2, but it may not be equal to I1 plus I2. In fact, it is found that the resultant intensity at point P may be greater than I1 plus I2. It may be greater than I1 plus I2. Okay? And it is also possible that the resultant intensity I is smaller than I1 plus I2. Okay? Actually, what is the reality? We will see just when I will teach you in this lecture the basic theory of interference. But before that, I am writing that result directly here so that you can understand the definition in a concrete manner. What actually happens? Actually, at the point of superposition, resultant intensity is not fixed. At different point, the intensity will be different. It is not always I1 plus I2. As I have told you, this may be greater than I1 plus I2, or this may also be less than I1 plus I2. In fact, at any point, the intensity has two limits. its minimum is fixed, maximum is also fixed. It means actually at a point the intensity oscillates in a periodic manner. We will see later on. Intensity varies periodically or it oscillates. And during that oscillation, the maximum intensity at the point of superposition is equal to a square of root over I1 plus root over I2. Or you can say I1 plus I2 plus 2 times of root over I1 I2. This is actually the maximum intensity that can be possible at the point of superposition. Resultant intensity at the point of superposition is never greater than this maximum value. In the similar manner, it is also found that at this point of superposition, the minimum value of resultant intensity is given like this. This is a square of root over I1 difference root over I2. In other words, we can say the minimum intensity at the point of superposition is found I1 plus I2 minus 2 times of a square root of I1 I2. So intensity at that point of superposition is never less than this value. But you can see this minimum value of intensity is less than I1 plus I2 because here 2 root over I1 I2 has been subtracted from I1 plus I2. On the other hand, you can see this maximum value of intensity is greater than I1 plus I2. So in fact, the intensity, and when you say intensity, you may also call energy because you define intensity as the energy passing through unit area in unit time normally. So the intensity or energy distribution is not uniform, but it becomes non-uniform in the region of superposition of waves. So in the region of superposition of waves, at different point intensity is different, not uniform. Okay? If you will talk about the light wave, in case of interference, then when two light waves will interfere, will meet together, it is found that it is not always more light, but at the point of meeting of two light waves, there may be darkness. Okay? There may be darkness. So, as a whole, you can say that in the region of superposition at different point intensity is different. Although I have told you that this variation is limited. It is this resultant intensity is never less than this minimum value and it is never greater than this maximum value. But between these two limits, intensity varies from minimum to maximum and maximum to minimum. So you can say that as a whole in the region of superposition, the distribution of energy or distribution of intensity becomes non-uniform. Actually, this phenomenon of modification of intensity due to superposition of two or more waves is known as interference of wave. This is called interference. And if you are talking about the interference of sound, then you should say that this is interference of sound wave. If you are talking about interference in light waves, then you will say this is interference in light wave. Okay? Now, you have seen that actually at some point intensity has its minimum value, which is given by this expression, a square root of I1 difference I2. You can also write minus sign here instead of difference. Okay. Actually, the points where resultant intensity is minimum, that you say that destructive interference is taking place at that point. Where destructive interference takes place? Can you say? Definitely you can say. All those points where intensity is minimum, you say that destructive interference has taken place at those points. In the similar manner, those points where intensity is maximum, that is intensity is a square of a square root of I1 plus a square root of I2. At those points, we simply say that constructive interference takes place. So the constructive interference and destructive interference, these are two important terms, and we will discuss these constructive and destructive interference after the basic theory of this interference in very detail in our next lecture. Okay. Actually, all these formula which I have mentioned here for your convenience to understand the definition of interference, I have written directly without any proof. But now we are going to see how you can say that minimum intensity is this much and maximum intensity is this much. How you can say. And for this, we have to see the basic theory of interference. So now we are going to analyze this phenomenon of interference in analytical manner or in mathematical manner. Okay? Or you can say this is the basic theory of interference. But the final result which we will obtain in this basic theory of interference, which explains the interference clearly, but complete explanation will be in next part of the video. Here our prime aim is to derive the final result to explain this interference. Okay. Now let us see. Again I have shown here in this figure, there are two sources of wave. These may be sources of sound wave, these may be sources of light wave. One is S1 and another is S2. Okay. And we consider that these two sources are separated from one another by a distance small t. And this is a screen, or you can say a detector. A screen or detector where interference will be detected. Okay. And the distance of the screen or this detector from the plane of this source is capital T. You will learn in that when I will discuss the result that it is an experimental requirement for the sustained interference that this small d must be much smaller than this capital D. It means in general, if you take this capital D in the order of meter, then this small d is in the order of millimeter. Okay? And if a small d is in the order of, let us say, meter, then this capital D should be in the order of kilometer. Then interference will be sustained. Interference will take place, but if you want to observe the sustained pattern of interference, then this condition must hold. Okay? So you can say that actually the sources S1 and S2 are placed very close to one another, very close. Okay? Now, waves will be emitted from both of the sources. We consider that both sources produce wave of same frequency omega. Omega is the angular frequency of the wave produced by the source S1 and also by S2. Okay? And as S1 and S2 are very close, so you can say that the waves produced by S1, S2 will move almost in same direction. Both waves are collinear, you can say. And such two waves from S1 and S2 get superposed at this point P, as you can see in this figure. Okay. Actually, I have shown here that before reaching to the point P, the wave from source S1 covers a distance x. It means I have assumed that S1P is equal to x. Okay? And the wave from S2 reaches to point P, and before that, that wave covers a distance S2P, which we have assumed x plus delta x. Okay? Although these two waves are moving almost in same direction because S1, S2 are very close. So you can see that S2P minus S1P, this will be equal to delta x. This is actually called path difference. It means before reaching the point of interference, the second wave covers delta x distance greater than that of the wave from source S1. So this is called path difference. In fact, we also assume that when the waves are produced from sources S1 and S2, then those two waves are in same phase. Their phase do not differ. The phase of the wave from source S1 and the phase of the wave from source S2 at initial moment when they are produced are equal. But due to this path difference, you will see later on that when the wave will arrive at this point P, there will be a phase difference introduced between them, and the reason of that very phase difference will be this path difference delta x. So due to that path difference delta x, now at point P, the two waves will have a phase difference. Okay. Now the two waves actually superpose here, and after superposition of the two waves, a resultant wave will be produced. So first part of our problem will be what? First part of our problem will be to find that resulting wave. And when you say we will find the resulting wave, it means you have to find the analytical equation which actually defines that resultant wave. And for that, you must know about the first superposing waves, first and second superposing waves, and then by using the principle of superposition, you can easily find the equation of the resultant wave. You have actually studied this superposition principle in case of vibration in very detail. So actually what I have explained, I have mentioned it here. You can see that this delta x, which is path difference between two waves at P. Okay, and as I have told you that if initially the waves are in same phase and have amplitudes A1 and A2, A1 is the amplitude of first wave, A2 is the amplitude of second wave, then these waves are represented like what? The first wave will be represented by psi1. Here psi1 is actually the wave function, or you can say the displacement of the particle of the medium at position x and time t. And this psi1 will be given by a1 times sine of omega t minus kx. This k is the wave number, or this is the wave vector. And psi2, which is the wave function of the second wave, that will be given by a2 times sine omega t minus k times x plus delta x. For the second wave, x is equal to x plus delta x. And so psi2 is equal to a2 times sine of omega t minus kx minus k times delta x. Now, instead of this k times delta x, we can write phi. But k, which is the angular wave number or the wave vector, that is related with the wavelength of the wave by this relation 2 pi by lambda. So phi is equal to 2 pi over lambda into delta x. Actually, you can see, if I will ask you what is the phase of the first wave at time t and position x, or you can at time t, your answer will be omega t minus kx. This is the phase of our first wave at time t. Now I ask you another question. What is the phase of the second wave at the same time? Your answer will be this much. Omega t minus kx minus phi. Minus kx minus phi. Are these two phases equal? Answer is no. There is a difference between these two phases by phi. So actually, what is this phi? Phi is the phase difference between the two superposing waves at the point of superposition P. Okay. Now, when these two waves will get superposed, a resultant wave will be produced. and by principle of superposition, that resultant wave is given by psi equal to psi 1 plus psi 2. It is a common fact which we have learned several times earlier. Okay. Now let us substitute the values of psi 1 and psi 2. You know, psi 1 is this much, a1 times sine of omega t minus kx. And what is psi 2? This is a2 times sine of omega t minus kx minus phi. Okay. Now keep this first term at each and expand sine of omega t minus kx minus phi by using the formula of sine a minus b. Here we will treat this omega t minus kx as a, okay, and phi as b. So this will be sine a minus b. And I hope you have a knowledge of the formula for sine a minus b. This is sine a into cos b minus cos a into sine b. So utilizing that very formula, this term will be sine omega t minus kx times cos phi, okay, minus cos omega t minus kx times sine phi. Now let us see this sine omega t minus kx and this sine omega t minus kx. When you will associate these two terms, you can take this sine omega t minus kx as a common factor. So after taking sine omega t minus kx as a common factor, the multiple remaining will be a1 plus a2 cos phi. Okay. Now see the last term. Last term is minus a2 sine phi times cosine of omega t minus kx. Okay. Now to cast this equation in a convenient form, let us substitute a1 plus a2 cos phi, which is present here, equal to a cos delta. We assume it. Okay. And a2 sine phi, we assume that this is a sine delta. You can see this is our supposition. You don't know this a. You also don't know this delta. Okay. So we must evaluate the value of a and this delta. Actually a will be the resultant amplitude, that is the amplitude of the resulting wave, you will see later on. But before that, let us substitute the value of a1 plus a2 cos phi and a2 sin phi from equation 4 and 5 in this above equation. Okay. So you can see psi will be then equal to a sine omega t minus kx times cos delta and minus a cos omega t minus kx into sin delta. Now again see this expression. Again utilizing the formula for sine a minus b, if you treat this omega t minus kx as a and omega this delta as b, then you can write that this expression will be psi equal to a sine omega t minus kx minus delta. Okay. Actually this equation represents the resulting wave which is produced by the superposition of the two waves from the sources S1 and S2. Now you can see that this resultant wave has amplitude A. This A is the resultant amplitude or the resulting amplitude of the resultant amplitude or the amplitude of the resultant wave. Okay. And omega t minus kx minus delta is its phase, and you can see this resultant wave also differs in phase by this delta from the first wave. Okay. But in this equation, you know, you don't know the value of a and delta. So first of all, now we will find the value of a and delta. Okay. For finding the value of a, what you will do? See this equation 4 and 5. You know, in these two equations, there are two unknowns, a and delta, and we have also two equations. As we know, we have to evaluate two quantities, and containing those two quantities, we have two independent equations, so we can easily evaluate them. If your aim is to find A, you must eliminate delta. And how you can eliminate delta? See the algebra. When you will actually square equation 4 and 5 and add together, you will get the value of A and delta will be eliminated. So let us see that after squaring those two equations, we will have A square equal to A1 plus A2 cos phi whole square plus A2 square sin square phi. Now, after simplification, you will have A1 square plus A2 square cos square phi, and here there is A2 square sin square phi. So when you will take A2 square as a common factor, then the remaining term will be 1, because cos square phi plus sin square phi will be 1, and the third term will be 2A1 A2 cos phi. So the resultant amplitude A is given by a square root of A1 square plus A2 square plus 2A1 A2 cos phi. So this is the expression for the resultant amplitude. This is actually a most important result. For discussion and for solving the numerical problem based on the interference, you must remember this result. Okay. Now another unknown was delta, which is phase difference between the first wave and the resultant wave. And you can see, if your aim is to find delta, you must divide this equation 5 by 4. When you will divide equation 5 by 4, then you will get tan delta equal to A2 sin phi over A1 plus A2 cos phi. So by this equation 8, we will obtain the value of delta. But the value of A, which is defined in this equation A, this is the equation of our interest in present situation, because you will see when we will discuss the phenomenon of interference, this will be the basic equation. Okay, and you can see from this equation number 6. Now I will ask you, this equation 6 is equation of a harmonic wave or not? Answer will be yes. This psi equal to A sin omega t minus kx minus delta, this is the equation of a harmonic wave. And this harmonic wave is actually the resultant harmonic wave. And one thing is very interesting here, that frequency of this harmonic wave is same as that of the frequency of superposing wave. So you can say, if two waves of equal frequencies get superposed, then the resulting wave produced has the frequency equal to the individual waves. But what about amplitude? Let us see. The amplitude of the first wave was A1, second waves was A2, but the amplitude of the resultant wave is neither A1 nor A2 nor A1 plus A2, but it is A, which is defined in this equation 7. This is a square root of A1 square plus A2 square plus 2A1 A2 cos phi. Okay. In fact, as cos phi is present here, and you know cos phi is actually a periodic function. Its period is 2 pi. After 2 pi interval, it repeats its value. And it always varies between -1 and +1. These are the limiting value of cos phi. So definitely the resultant amplitude of the wave or the amplitude of the resultant wave is not constant. It depends on the phase difference between the superposing waves. And you have seen that this phase difference phi actually depends on the path difference. So in accordance with change in path difference, change in position of the point of superposition, phase difference will change, and when phase difference will change, resultant amplitude will change. Okay? But in terms of resultant amplitude, you cannot talk about the resultant intensity, which I have mentioned in definition of interference. Actually, you know, in case of any wave, the intensity of the wave is always proportional to the square of the modulus of amplitude. Why modulus? Amplitude of a wave may be complex. So when amplitude of a wave is complex, let us say A, then you have to take a constant k times mod of a square, or you should say that k is equal to a into a star, where a star is the complex conjugate of a. Okay? But if amplitude is real, then there is no need to write this modulus sign. In present case, we have seen that the the amplitude obtained is real. So here it is not very meaningful. But in general, intensity of any wave is proportional to a square of the modulus of amplitude of the wave. And in a standard textbook, the proportionality constant, this k is taken to be 1. So roughly we simply say that intensity is equal to a square of the modulus of amplitude. But I have written here that I is proportional to mod a square. And when you will remove this sign of proportionality, you write the proportionality constant k. You may take it 1. Oh, you may take it 1. But I have not taken here 1. I have written k. And you know, a square will be this much, a1 square plus a2 square plus 2a1 a2 cos pi. Now this can be written as k times a1 square plus k times a2 square plus 2. Now see here. Here there will be 2k a1 a2 cos pi. But I have written it a square root of k a1 square times a square root of k a2 square. I have written the same thing, but in different manner. A root over k and root over k, that will become k. And a1 square and a2 square have been written inside the square bracket, inside the square root. So that will be a1 and a2. So this can be written like this. But as you know, that k a1 square, a1 is the amplitude of the first wave. So k a1 square will be the measure of intensity of the first wave, which is denoted by the symbol I1. So instead of k a1 square, I have written here I1. Okay. Similarly, intensity of the second wave I2 is given by k times a2 square, because a2 is its amplitude. So instead of k a2 square here, I have written I2. Okay. And again, inside the square root there is k a1 square and k a2 square. So here there will be a square root of I1 I2. So finally we get that the resultant intensity after the superposition of two waves is equal to I1 plus I2 plus 2 root over I1 I2 times cos pi. Okay. So you can see, is this resultant intensity equal to I1 plus I2 in general? Answer is no. But it may be equal to I1 plus I2. When cos phi is equal to 0, or you can say when phi will be equal to pi by 2, or 3 pi by 2, or 5 pi by 2, then cos phi will be 0, or I will be equal to I1 plus I2. Okay. But in general, you can't say that when the two waves of intensities I1 and I2 get superposed, the resultant intensity will be I1 plus I2. You can't say. Okay. So I have mentioned it here. You can see that it is clear from this equation that the resultant intensity at P is not just the sum of intensities due to the individual waves, that is I1 plus I2, but different and depends on the phase difference phi between the waves at P. And you know, phi is 2 pi by lambda into delta x, and delta x depends on the position of P. So at different position, delta x will have different value, and corresponding to different value of delta x, phi will have different value. And therefore, the intensity in the region of superposition will vary point to point. And so in the definition it has been told that the intensity distribution becomes non-uniform in the region of superposition. Okay. Again, you know, cos phi is an oscillatory function. As I have told you earlier, this oscillates between -1 and +1. And you know, the maximum value of cos phi is 1. And from this result, it is clear that when cos phi will be maximum, then I will be maximum. So, putting cos phi equal to 1 in that result, you will get the maximum intensity. And what will be that? That maximum intensity will be I1 plus I2 plus 2 times of a square root of I1 into I2, because cos phi is 1. And that can be written as root over I1 plus root over I2 whole square. This result I have mentioned in the beginning directly without any proof. But now you know how we can say that maximum intensity will be equal to this much. Is it clear? Definitely you have understood. Now you also know that the minimum value of cos phi is equal to -1. So when you will put -1 at the place of this cos phi in this equation 9, you will get the minimum intensity. And what will be that minimum intensity? You can see that will be I minimum equal to I1 plus I2 minus 2 times of a square root of I1 times I2. Or this can be written as a square of root over I1 minus root over I2. Okay. Or you can say difference. Here I have written the sign of difference, but you may write minus sign too. Difference is written in this sense that if I1 is larger, then you will subtract root over I2 from root over I1. But if I1 is smaller, then we will subtract root over I1 from I2. So difference has been written. Okay. So this is how we can explain this interference. I hope you have clearly understand that intensity will not remain constant, but it will vary point to point in the region of superposition. But as I have told you earlier, after getting this result for resultant intensity and the resultant amplitude here, actually we will discuss the important facts regarding this interference. And that will be actually discussed in our forthcoming video. So definitely after watching this video, you must watch our forthcoming video for the completion of the concept of interference. Okay, thank you very much.